Hello everyone, present our work that has been done by my student Alison Lucena, and I am Luis Gonçalves, and basically he has developed a micro UAV, we call it brush, because it has basic or low risk operation for people and installation, and it is a self-handled platform. So here we show just the basic construction of it, and we believe this can be a good starting point for people who wish to work in this category of micro UAV. Basically, we have our motivation from two things. The first one is that a research project that we got from Brazilian sponsoring agents was awarded just to develop a small category of UAV. And this category is the last one here that we can see in this column, the last column, which summarizes the Brazilian laws, current laws on the operation of aircraft systems, of unmanned aircraft systems. As you can see in the left one, all of the requirements of are must be obeyed, of the rules must be obeyed. Of course, this is a huge UAVs above 150 kilograms, and we are in the other side with our aircraft weighing up to 200 grams. These are examples of the big sizes, small sizes, and very small sizes UAVs. In the big size category, for example, we have the Global Hawk and the Predator that both of them are developed for, are mostly used in surveillance by the armies and so on, in surveillance tasks or bomber tasks. We also have in here that we call the small size ones. The small size category, basically from 2 meters to the 6 meters. The basic application is on agriculture and surveying and so on, mapping. When we go to these even smaller ones, we call here very small UAVs. We have two of them here that we're using also by surveillance. However, we also have the ones used for topography and so on. Well, we are talking about even smaller than these ones. Besides, you can consider from 1 meter or less in this category, the micro UAV. Well, here we can see the one that was in the other page. Actually, in this category, we could find one of the first one was the Black Widow. Actually, this goes from here to there and not from here to there. I put in this because of the bigger size and going to the smaller size. But the first one developed was this one, and it was further renamed. The project was further renamed to WASP, and where they built a 33 centimeters one with 107 grams. But I mean, I think this one had not that much applicability at that time. So from this one, they could have some good applicability in the beginning of this cycle. One of the smaller one that we can also that have similar capabilities as ours is the Black Hornet. It's here, besides it's not a fixed wing one, so this limited its operation of about 2 kilometers, no more than that. And also we can cite here the mosquito that was developed for Israel arm. And it is, the first one was about 33 centimeters, actually this is wrong in here. And the second one is 35 centimeters, weighing 500 grams. So this is outside also. We want even a smaller one than these ones in here. That's the objective of our project. So we starting developing some prototypes. Actually, we have built several of them in order to reach our current one. We went to 90 prototypes with several aircraft built in each one of them. Several of them were destructed. This is actually a very empirical study that we have been done since 2012 when we got this project, and currently we got it developed in full. Actually, in this prototype, for example, it has 30 centimeters of wingspan, and it's made of this is a massive wing, and also it has a massive body in here. The Epler 423 profile was used in here, and it worked well inside. However, we have had problems outside. This must because the flow of wind in the extremity of the wings cause problems, so it makes it very unstable. The prototype number 5, for example, is this. It's already a delta wing with 30 centimeters and 11 centimeters of medium hope. And this is a KV-like fuselage. And the most important here is that it worked well inside, but we had some problems outside because of mainly of the surface are plane. So we didn't have we have problem with stability. With arrangements on it, this type can work better outside. That's what we did in the next. You can see this one approximates the smallest one with 16 centimeters that I showed previously. It did not work because of the disturbed flow that interferes with the pressure distribution of the wing. So this makes it very unstable. In this case, when we diminish the small size ones, is really, I think everyone knows that, is really a problem to make it unstable outside. We have chosen a delta type, as that one worked a little better. We have chosen this delta wing type and for the construction. Then we went for some tests first for simulation, and the tests on to verify the flow and so on in this. All of them we did that, but this one is the one that we have chosen for as our prototype. Here we can see the model that we did using a CAD, and we can see the surface, the control surface in the back. One of the important things in this prototype is that the propeller is at the aircraft center. This is one of the reasons for it not being danger, not putting people in problem. If this hits some person, it's not going to produce damage as if the propeller is in the front, for example. It can have, we actually have 2 servos that can produce pitching up and down, and it also can produce rolling to the left and to the right when we put one in each one of them in one opposite directions. About that. Okay, the control surface in conventional situation should be like something like this, for example. And so with this, we got more control of it. We found a better control. This is the dimensions of our aircraft. As you can see, it has 25 centimeters of wingspan, and it's about, if you consider the tail here, we are going to have 25 centimeters too. And as I said, the propeller is at the center. This is, in fact, one of the characteristics that we went behind it, because we want not to produce damages to people. I mean, this now can be very safely operated with no problem to installations or to persons who would be in the theater, in the area of operation. This is the back profile of it. We have this stabilizing surface in degrees inclination, and both of the sides have also a 10 degrees of inclination in relation to the plane. We went to wind tests on this on a CAD model. With that, we determined that it produces some force when it gets to building this back profile, when it gets close to the extremities, but that's okay. That does not interfere in the outside. That did not interfere in the outside flights that we have done, and as you can see later, it worked well on that. Okay, so we have done this for every of the prototypes that we built, and here we show this for this one, which is the best one. Here we can see the material that we used to build it. Basically, we have a motor, and we have two servos that are also responsible for the movements, for directioning it there. This is a one battery configuration, but we also tested a two batteries configuration, and we believe that it can fly even with a three batteries configuration. With a three battery, it can go to some 30 to 40 minutes of operation after some enhancements that we have to do on the engine. In this version, it has a receiver, because we should have the possibility of controlling it, but we also have a autopilot to be embarked, and we didn't do a test with this autopilot yet, but it's ready for it. Actually, we have done several other UAVs. In one of them, we tested this autopilot, and it worked well. And so we have all of the capabilities for putting this in the current prototype. This is the construction of it. From zero to this, we took about 40 minutes to 40 to 50 minutes to the final assembly of it. As you can see, the autopilot is not here yet. Okay, so after that, we went to thrust. You can see here we have 74 grams. When it reaches about 2000 RPM, rotations per minute. After this, we went them to testing, first with indoor flights. In this indoor flight, we didn't turn on the stabilization, and we put just the it running with the motor in a certain at 40% of acceleration, just to test if it went to do a straight line. Actually, it bended to the left, and then we had to do some corrections for this. Actually, the first wing that I showed to you, in some occasions when we accelerated a little, it started turning a rotation left. So this one went to this test, and after that we have repositioned the center of gravity of it, putting a little back that payload box, and then it started working better. Okay, after these indoor flights, we went to several outdoor flights. And here I show just some pictures that we took from one of these flights that had about 4 minutes of operation. And actually, we noticed that this is very extremely windy conditions. This is Natal, the northeast of Brazil. And here we can have wind, constant wind, and then hurricanes of about 15 to 13 knots, and the wind is about 10 to 20 knots. So this is one of the extreme wind conditions. And it was very stressed tested in this condition. So I think it's okay, it's good now. Here, of course, we had stabilization on it, and it worked well. So the next steps is to put the autopilot on it, and we have built and also we have bought a image acquiring equipment for doing videos. So that's it. I thank you very much, and I am open for questions. If I cannot answer, I will transfer them to Ellison, and I think he can answer all of you. Thank you.